Okay, so first things first, I would like to thank Christina and all the organizing for putting this conference together. We know that's contrary to what you said. It's a little bit difficult to bring all these people from different communities on the same date. And I think this workshop so far has been magnificent. There's I was able to collaborate with a diverse range of people who I have never met before, doing different things. So I think that was very nice and inspiring at the same time. So as Christina said, the title of my talk, what I plan to cover is essentially the usage of magnons for quantum information science. And so I'm Denis CANDIDO, and I'm professor from the University of Iowa. And if you guys are wondering what the heck is that, so we are in the Midwest. So 3 hours approximately by car from Chicago, because we don't have train. Otherwise, it would be faster. And University of Iowa, or Iowa City, it's a kind of beautiful city. So here there's some pictures of it. And the winters are harsh though. And although they're a little bit sunny, so it's kind of makes us feel a little bit better. And if you're interested in literature, Iowa City is the UNESCO City of Literature. So there's some annual workshops there that happens, and it's kind of super nice and cozy and charming. And so here, this is the river that we have there. It's named Iowa City River, and this is our building. So if you just give a zoom, so this is the place where we have our offices, and the experimentalists have their lab. So this is called Iowa Advanced Technological Laboratories. Even though it's advanced, sometimes it leaks, but that's all good. And it was designed by the very well-known architect Frank Gehry. So anyway, so I always would like to start by thanking my collaborators. And here we have Christina and Ilse, my PhD students, who presented a poster on Tuesday. So without the contributions from all these people here, none of the works that I'm going to be presenting here would be possible. So this is essentially the outline of my talk. I intend to first talk about spin defects in solid-state physics. Then I'm going to talk about why they're good, but at the same time, I'm going to talk about the problems that they face. Then I'm going to talk about how we plan, or how we propose to solve this problem. And later, I'm going to move and talk about something that's more in the spirit of this, well, everything is in the spirit, but this one is more timely, let's say, because it talks about how to entangle quantum experiments. And this is done in collaboration with Christina, and also some very recent results that we have on imaging of vortex magnetization using spin centers in HBN. So without further ado, let's get started. So spin centers or spin defects in semiconductors. So these are essentially structural defects of the lattice. So we have already seen some talks talking about the nitrogen vacancy center defects in diamond, but that's not the only one. We also have die vacancies in silicon carbide, and these defects are also present in 2D materials, which is very convenient for integration aspects. So in terms of this quantum capabilities, if you take a look at recent published papers, the coherence of this system is enormous. Okay, so it's super long, reaching even seconds of coherence time. So this promotes them as a great candidate for solid-state qubits, and also for quantum memory and quantum information processing. So today I'm going to focus. But before doing that, I also want to mention that since these qubits, they are also sensitive to magnetic, electric field, and strain, they can also be used as a quantum sensor. And here I'm showing essentially 3 different works where the sensing of magnetic degrees of freedom was performed using NV centers. Okay, so the NV center, the spin center that I'm going to be focusing on this talk is the nitrogen vacancy center in diamond. So this corresponds to have a nitrogen atom on place substituting a carbon atom, followed by this removal of an adjacent carbon atom. So this forms this nitrogen vacancy center, and the electrons stay confined here. And if we take a look at let's say the energy level of this, so the ground state is a triplet. So this is already interesting because it's not a qubit. We have actually 3 levels, so we can have more degree of freedom to play around it. And most importantly, this energy level, it's already split without applying magnetic field. So this is called the zero field splitting, and its nominal value is around 2.8 gigahertz, which is also very convenient if you want to do operations and manipulations with of your qubit. And of course, here you can do that with microwave, so very convenient. And but of course, if you want to apply a magnetic field, this system is going to respond. So we have like a Zeeman splitting around 20 megahertz per millitesla, so very sensitive. So, but what I think is more interesting about the system is actually the optical initialization and readout. So, meaning to initialize and to read the state of this qubit, we just need to use a laser, okay? And this was essentially discussed thoroughly during Samuel's talk last on Wednesday, I think. So I'm not gonna like dive too much on it. But okay, so so far I have only been talking good stuff about this spin center. So what is the problem? Well, if we wanna do, let's say, implementation of quantum technology or quantum computing with this solid state qubits, we have to fulfill the Vincenzo criteria. And in principle, we are able to get all those four right away, but we face this problem with scalability. And in simple words, what that means is that one qubit, it's nothing against a classical computer. We need many qubits, and not only many qubits, but we need like many entangled qubits. So the natural question is whether we can couple and entangle two NV centers. And if you think that they are essentially like spins one entities, of course, magnetic dipole-dipole interaction are going to couple them. If you have them separated by 20 nanometers, this gives roughly a coupling strength of 10 kilohertz, which is like much faster than the decoherence that happens in these systems, and therefore, this is going to be in principle able to entangle and couple NVs. However, if you remember, to initialize and read these qubits, we need a laser. And when I show essentially like this picture here, this is essentially a little bit misleading, because when I try to address or initialize one qubit, instead of having this very like tiny laser beam, I actually have like this one. So the spot is around like 500 nanometers. So which implies that while you try to address NV number one, or you try to read NV number one, you're going to be messing up with the other. So the question is, how do we couple and entangle NVs at distances in which they can be optically addressed and read? And this is the main topic of my talk, and I plan to do that using magnonic systems. So this kind of like that general idea, it's not new. So this is what people call like, we need to mediate or assist the interaction between two objects. And you can do that with what people in the field call like quantum bus. We know that the best quantum bus are essentially like the bosonic modes. So of course you can do that with optical fibers and photons. And this here, we have this nice experiment by Hansen in Delft, and this proposed also by Denis was using like magnets instead of photons. Okay, so hybrid magnonic quantum systems. So that's the main topic of my talk, and this is how I plan to, let's say, overcome this inherent problem of NV centers. And this is essentially the two first works that I'm going to be talking about. So first thing first, there are essentially like three main ingredients that we need to reach or obtain in order to push this proposal forward. So the first one is coherent NV center spins. And of course, we have that, right? I have shown you that spin centers are very coherent up to seconds of coherence time, but most reasonable values are around the millisecond, which is good enough for this purpose. So the second point is coherent magnon modes at low temperature. And this is like a little bit more tricky because we need like super low loss materials. There are a few of them, like for instance YIG, but here I want to open your mind for a different material that's called VTCNE, okay? And so this material is an organic ferromagnetic material, and it was the first material we tried to push this proposal forward. So saturation magnetization of 100 Gauss, but damping of like comparable to YIG, 4 times 10 to the minus 5. So very interesting material, and we are able to characterize the line width at super low temperature, which is going to be actually critical for this proposal. And then you can see that even though the line width increases for low temperatures, you can see a sudden drop around like 5 Kelvin. So, and then we expect our model fits this very well. Then we expect the line width at low temperatures to be around like 1 or 2 Gauss. So this material suffices. And just like doing some advertisements about the potential of this material, where we measure the spin-Seebeck resistance and we obtain like valuables comparable to YIG, even though the saturation magnetization is like 1 order of magnitude smaller. So this is going to be the material I'm going to try to pitch this idea, although I'm going to show the same thing can be done with YIG. So the third ingredient, it's actually strong magnon NV coupling. Okay? And this is what I'm going to like try to digress a little bit more. So when I take this magnetic material, I make a disk of it, and I try to solve the modes. So the modes I'm going to be interested, it's this kind of whispery gallery modes, because their magnetization is localized on the rim of this disk, which implies that the amplitude of the fringe fields coming out of this magnetization is going to be more pronounced, just because of like essentially normalization aspect of the magnonic profile. So if I calculate the coupling for this angular mode, I get like 10 kilohertz, which suffices for this purpose, as I said before. And this is essentially the on-resonant Hamiltonian for this system. And the physics of this system, it's kind of like fine. But since we're talking about on-resonance, I have to just like verify whether I do obtain a resonance condition. And this is like a plot of the NV frequency transitions as a function of the magnetic field, where and here the black ones are just like the magnonic modes for these angular modes here. And of course, we can see that around like 55, 56 millitesla, we do have a crossing. So the resonance condition is achieved in the system. So now let's just understand the physics underlying this model here, and things are like super simple. So suppose you have an NV center 1 into the excited state, then NV center 2 in the ground state, and let's say a few magnons or like no magnons to simplify. So, and you let this system evolve. So if you do that, so the first thing you're going to take a decay, a lowering of this spin subspace, and then the excitation of one magnon. Then this magnon is going to start interacting with the second magnon, and after some time, you're going to excite this. So this is essentially like the swap operation, and this essentially gives us like entangling measures of entanglement, as I'm going to show next. So, but back to the strong coupling regime. What does that mean? Well, so we characterize the strong coupling regime via a parameter that's called cooperativity. And cooperativity is essentially the ratio of the spin, the magnon spin coupling divided by the magnon damping rate times spin coupling, spin magnon coupling divided by the dephasing time of the NV center. So strictly speaking, what this cooperativity gives us is like how many times we can swap information from your NV to the magnon without losing the information within any of these entities, okay? And of course, to achieve this strong coupling regime, we need cooperativity larger than 1, okay? So then if we plot this cooperativity here at minus 80 nanometers below the disk, this is the cooperativity map. And then we can see that we reach values of cooperativity around like 30, which suffices for this purpose. But most important, we can see that we get cooperativity when NV centers are placed very super close by the rim, okay? So why is this important? Because, well, this is important because we want to use laser to address those two NV centers individually. So we need them like very far from each other. So if we put one NV here and the other NV here, they're going to be distanced by approximately 800 nanometers. And that essentially like is sufficient for us to address NV center spins individually. The other thing we have to concern about is to avoid the noise coming from this like interface here. And we do that by plotting the cooperativity as a function of the z direction, so cross-sectional plot. And then we see that we get cooperativities up to 2 or 3, even like at 90 nanometers below the surface. So in that way, we can avoid the noise coming from this interface of the surface. So that's like all good. And of course, this is for VTSNE, so you can ask, well, why don't you do that with YIG? Well, we did. Actually, we were able to derive like a cooperativity formula that depends on the NV parameters, only geometric parameters here, and then the properties of the magnetic material. So, and of course, as I mentioned to you before, YIG has a larger saturation magnetization, so in principle, the cooperativity should be stronger. The problem is, we need like thin films to enhance the stray field of our magnon modes. And YIG under like thin film configurations present like a larger damping, okay? When we wrote this paper, I think this was like the best Gilbert value for YIG films. And then if we use this one here, then we get cooperativities up to 6, which is not super good. However, if we use the bulk value, then the cooperativities go up to like 200, kind of overperforming the spin center. Oh, sorry, the VTCNE. Okay, so with having met all these like 3 criteria, we kind of like can successfully claim that this proposal might work, and people essentially got excited about this type of like system, and influenced even by the color scheme that we used, and people started ready to push this kind of like experiments like forward, and this is just like one example of it. So, but what about, can we generalize this for other systems, other proposals, other geometries, anyway, other configurations? And the answer is yes. And this is what we did in this follow-up work, where we used like a slab of YIG, now with an in-plane magnetic field. Again, we did the same thing. We calculated the resonance condition, and we found one. We calculated the NV magnum coupling. This gave us like 500 megahertz, so 500 kilohertz, or 1 order of magnitude like greater than our previous scheme, and cooperativity around like 50,000. So that was all good, but what we did in this work that was like most interesting was to simulate essentially like entangling protocols using like really realistic protocols. So of course we had to employ the Lindblad master equation for 2 spin centers communicating through the bath. And this is the own resonant protocol that we used. So to essentially describe this very quickly, we start with NV1 and NV2, far detuned from our magnum mode here. Then we first bring NV2 in resonance, let it evolve for a time t-var. So this is essentially going to entangle the spin with the magnum. Then we bring NV2 far off resonance, and then we bring NV1 in resonance. Okay, so in the end, what we have is the entanglement of NV1 and 2 mediated by these magnum quasi-particles. This is the ideal state. Then what we do is we calculate 3 different measures of entanglement, so negativity, fidelity, and Bell's violation of Bell's inequality, and then we get like a positive number for all of them. So this is done at 70 millikelvin. So this you can see just like the swap of the excitation, and this decay here is essentially given by the lifetime of the magnons. So this is the own resonance protocol. So if you think about magnons, they have like short lifetimes. So the next thing we thought about was to use actually virtual magnons or have an NV of resonance to avoid exciting these magnons. And this is what we did in this off resonance protocol. And when we do so, well, then we can see that due to this like off resonance character of this protocol, all the entanglement measurements are much greater than the on resonant one that we found. However, we had like some very interesting discussions with experimentalists from quantum computing fields, and they talked that what they were like telling us is that even though this one presents like larger fidelity, so the gating time that it requires for you to achieve this entangled state is like much longer. So for instance, here we have like almost like around 4, while here we have like 0.4, so a factor of 10. So what does that mean? Well, it means that perhaps the on-resonant could be even better because you can attempt multiple times to do this, to employ this protocol and get a good result. So it's not like super clear-cut that the off-resonance is the best one. Okay, so then we tested the robustness of this entangling protocol as a function of temperature, and then we saw that actually off-resonance survives up to like 300 millikelvin. So for this temperature robustness with respect to the temperature, this off-resonance is a little bit better. And then what we did was the experimentalists are going to laugh now, but what we tried to do was to put a very low Gilbert damping of around 10 to the minus 7, because why not? And then if we do that, then we get fidelities at room temperature, at 1 Kelvin, fidelities of around 99.9. So very nice. So, and I think that the takeaway message of this slide here is that we should really push forward for trying to find very low loss magnetic materials. So this is a question that people ask me a lot of times. Well, we're going to have a spin bath. You're going to have like magnons. So besides mediating the coupling, this is also going to induce relaxation and dephasing. And that's actually true. That's why we calculated, for instance, the T2 induced by the presence of these magnons. And the values that we get are around like 100 of kilohertz. And this does not beat the magnon relaxation rate, which is around like 10 megahertz. So therefore, this is not like very important for the dynamics of the system. Okay, so now I essentially described the main results contained within these two papers. And the question now is whether we can like measure this experimentally. Can we like verify any of this? Actually, the answer is yes. And to essentially like first evidence the magnon and V coupling in experiments, what we do is to essentially recall that when we have like a spin or a qubit coupled to a continuum, if you remember your many-body class, this is going to have like a corresponding self-energy. The real part of the self-energy is going to shift the energy of the qubit. The imaginary is going to give rise to the broadening lifetime. And so essentially, we can estimate the magnon-induced lifetime due to the presence of the bath. And that's what we did theoretically, and that's what they did experimentally. And this is like the relaxation rate as a function of the magnetic field. And as you can see, the system relaxes super quickly when we have magnetic fields around 82 Gauss. So the question that we were like trying to answer at that time is, why does the relaxation peak at this value? And then we did like some magnon calculations, and we were able to verify that at 82 Gauss, the NV frequency is in resonance with like magnon surface waves. So this is essentially why this is happening. And then we developed like a whole relaxometry theory for this. And there's only one fitting parameter, which is the saturation magnetization. And we believe the theory fits very well. Oh boy, fits very well. Time flies. Fits very well like the data. Then we just like compare this with like further parameters, and it all matched. And then what we did after that was try to now evidence the magnon-mediated coupling between two spin centers. And to do that, we just have to remember that when we have two NVs coupled through like a magnon bath, the dynamics is going to be dictated by the Lindbladian, and the effective coupling between these two qubits, it's going to be given by this. And you cannot forget the Lemon-Stark shift, because magnons are like quantum fields. So it's going to renormalize the energies. Then what you had to remember is that the coupling between two spins actually is limited by the coupling when the distance of these two spins is 0. And this is just the self-energy. Or in other words, it's just the Lamb shift. So therefore, the coupling between two spins, it's limited, upper bounded by the Lamb shift. So then what we have to do is just calculate the Lamb shift. And we can, if we use the Kramers-Kronig relationship and the dissipational, the fluctuation dissipational theorem, we can relate the Lamb shift to the integral of the Fourier transform of our T1. And that's what we did. And then what we obtained, like when we calculated the self-energy, well, self-energy is ridiculous, like 2 hertz, so like super small. So that's essentially the upper limit for our coupling. Why super small? This is not useful at all, right? We're talking about like 10 kilohertz. So I'm only getting like 10 here. And the reason is like, here the Higgs sample was huge. So essentially, extended magnons, super small values of fringe field. But second one, this was done at room temperature. And the number of like magnets at room temperature is like huge. And what ended up happening is that when we tried to bring the NV closer to the magnon of Higgs slab, actually the T1 was so short that we could not initialize our NV center anymore. So we were kind of limited by the temperature of the system. Okay, so I hope I have 2 more minutes. 2 more minutes, okay. So after that, I'm also very interested in topological aspects of condensed matter, and this is just like a few of my works. But what we essentially, what I wanted to talk to you about now is to extending these ideas to explore entanglement using magnons in other systems. And this is like an ongoing work about to be finalized. in collaboration with Christina, where we tried to essentially use the Scherman qubits that she predicted in these two like very nice papers, and use magnum modes to entangle and couple them. So I'm just going to skip this. So essentially, these qubits, they are like basically defined on the helicity aspect of this qubit, and this is like very analogous to like photon polarization or the electron spin, or even like superconducting flux and corresponding qubits. So, so this is essentially like the Hamiltonian. But what I wanted you to focus is like actually on this like very complex, if you will, character of this two-level system. So this can be depending on how you tune the parameter. This can be either like what we call like longitudinal qubit, where the Hamiltonian is proportional to sigma z, or a transverse qubit, which is proportional to sigma x. Okay, and this is, as I'm going to show, this gives us like some nice degree of freedom with respect to how we're going to couple these two qubits. And this is just like some interesting materials where we think that they're the good candidates. And those are like frustrated magnets just because the Scherman energies, they live below the magnum continuum. So you don't want to have like magnons messing up with your skimmer. So that's why subgap energy Schermans are good. Okay, so then we calculated the spin magnum coupling. Sorry, the Scherman magnum coupling using this interlay exchange. This is essentially the effective interaction between both of them. And then what we could do is to find like two different limits for this coupling between Scherman qubits and magnons. One was the longitudinal, where we have this type of form, and the other one was like the transverse, which is like very similar to the NV work that I showed. Then we essentially like explore first the transverse. We calculate on resonant coupling, we calculate similar entangling protocols, we calculate Scherman magnum coupling, and this is like around 5 megahertz, just because of the closer proximity and the exchange interaction, exchange character of their interaction. And then we also did like of resonance coupling, very similar to what I showed today to you. And but what is interesting about this system is that we can even get like longitudinal coupling between two Scherman qubits, so namely sigma z, and of course if we have sigma z, then we just need to combine with single gates, and we can get the CZ gate, and then CZ gate plus Hadamard gives you like the C naught, and then you're also able to entangle. So this is going to be on archive soon, I hope, and yeah, with that I would like to thank you all for standing with me that long, and I'm more than happy to take any questions.